Hi, everyone. Welcome to Lecture 1 of Introductory Statistics. This first lecture is going to focus on graphing, in particular when we have just one variable that we want to graph at a time. Before we dive into graphing itself, though, we're going to need to go over a bit of terminology. So, the first term we want to think about is an observation. An observation is typically going to represent one row if we're looking at data in a spreadsheet. And if we're a little bit more precise, one observation is going to represent one unit in the data set. Now, exactly how we define what one unit is going to differ depending on the data set. A unit, for example, could be a day, right? If we have different rows of data that are different days in a year, for example. Or it could be a particular event, a particular object, or very commonly, it will be a single person. So if we conduct a survey, for example, and different people fill out the survey, each unit is going to be a different respondent, a different person who filled out the survey. Whenever we have a spreadsheet, if there are rows in the data set, there's also going to be columns, and that's what variables are. They're going to be the characteristics of those observations, and they can take on different values or amounts. So, for example, maybe we have a variable like gender, and some observations are going to be men, some are going to be women. Maybe we have some that are non binary or other, or maybe refused to answer. Those are all different values that this variable of gender can take on. And like we said, that's typically going to be a column of data if we're looking at data in a spreadsheet. Now, it's important to distinguish among different types of variables. And for now, we're going to focus on mainly thinking about qualitative and quantitative variables, and then we'll break that down a bit more. So, what is a qualitative variable? It's a variable consisting of categories that we can't obviously order in any particular way. And this is most easy to understand or easiest to understand if we have some examples. Things like race. You can have multiple racial categories like white, black, Latino, other, Asian. And there's no obvious, it's not like we can talk about least to most when we're talking about a qualitative variable. They're just distinct categories. Another example could be if we're looking at different organizations, maybe what industry that business operates in. Is it operating in manufacturing or in agriculture or technology? So, with this second example, now we're probably talking about a unit or an observation that is a business firm as opposed to an individual. If we go back to thinking about individuals, another variable that we might have that would be considered qualitative is pregnancy status, whether the person is pregnant or not pregnant. And this would be an example of a qualitative variable that can only take on two values, right? Either pregnant or not pregnant. Contrast qualitative variables with quantitative variables, which are variables where values have a numerical ordering. In other words, we can arrange them from least to greatest. What are some examples of that? Things like age, income, education level, right? We can say that one person is younger than the other person. In other words, we can talk about least to greatest. We can say that somebody has an income of $20,000 a year, whereas somebody else maybe has $35,000 a year, right? So we can quantify this. And really, what's important is that we can range from least to greatest. Sometimes it's hard to put a precise number on a value, but at least we can say that this person is more highly educated than that person or something like that. That's what we mean by a quantitative variable. Now, one note before we leave this page is that qualitative variables have some other names that they can go by, as are noted up here at the top of the screen. We can also call a qualitative variable a categorical variable or a nominal variable. And it's kind of unfortunate that we have multiple names for the same concept, but it's just important to be aware of because if you go to other sources, other textbooks, they might use these terms categorical or nominal instead of qualitative. So within quantitative, we actually want to subdivide quantitative variables into a few different types. So one of these types is called an ordinal variable. And it's a variable with values that can be clearly arranged from least to greatest, but where the distance between the values can't easily be quantified. It's a bit of a technical definition, but again, some examples are going to help. Thinking about things like education, right? And in particular, if we think about there's different ways you can code what education is, right? Like we could say, how many years of school have you had? And then it wouldn't be an ordinal variable. But in this example, I put in parentheses what the different values of that education could be. And let's say that, we just have some respondents, we see that they have high school diploma or less. And then for other respondents, we see that they have some college. Other respondents have a 4-year college degree, and other respondents have an advanced degree. So we can arrange that from most to least, right? The advanced degree respondents are the ones who have the most education, but it's not like we can necessarily say that someone with an advanced degree has twice as much education as somebody with a high school diploma, or that even necessarily having some college is the amount of additional schooling compared to high school diploma or less that you would get if you go from a 4-year degree to an advanced degree. In other words, it's not super easy to quantify exactly where you're at, but we can arrange people from least to most, right? Those who have more education, those who have less education. Another example of this is something called a Likert scale. And we see this a lot of times when it comes to attitudinal variables, asking people things like, what do you think of a particular politician? Or what do you think of this particular policy? Or how satisfied are you at your job? And a lot of times, the response options that people will have to a survey question like that are a range of values. For example, there might be a statement like, I love my workplace. And they can choose either strongly disagree, somewhat agree, or strongly agree. And then we can arrange those answers from least to most, right? Those who say strongly agree, they love their work environment the most. Those who say strongly disagree, they dislike their work environment the most, right? So we can arrange from least to most, but it's not so easy to put into numbers exactly what we're talking about. All right, that's one type of quantitative variable, ordinal variables. There are also discrete variables. Discrete variables can take on certain values within a range. For example, this is typically going to be whole numbers, but they're not ordinal. And that means that we can sort of quantify the distance between these, or generally just express clearly in numbers what we're talking about. So here are some examples. Number of children. It's a discrete variable because it can only take on whole numbers, right? I can't have 2.3 children, but I could have 2 children or 3 children or 4 children, and it's easy to quantify, but we have to restrict ourselves to whole numbers. Similarly, number of visits that I've made to the office in a week. That's something that is a discrete variable. I can only take on whole number values. Our final type of variable is a continuous variable, and this is a variable that can be measured to many decimal places, at least in theory. We might not always use all the decimal places, but if we had really precise measurement, we could. So some examples are weight, right? And again, a lot of times people report weight without using any decimal places, right? Somebody just says that a particular object weighs 32 pounds. But if they want to be more precise, they can go to several decimal places, right? They could say that the object weighs 32.378 pounds, for example. Income is another example, or response times, right? These are all things that we can quantify, and we can use lots of decimal places if we want to measure things very precisely. All right. Now that we've gone over different types of variables, we want to talk quickly about percentiles. And part of the reason that we're talking about this in a lecture on graphs is because some graphing techniques are going to rely on percentiles. So the basic definition of a percentile is that p% of the data is going to fall at or below the pth percentile. So this is again going to be easier with some examples, but let's say we're talking about the 25th percentile. Someone tells us, what is the 25th percentile of age in your data set? And you run the numbers and say, well, my statistical software is telling me that 30 is the 25th percentile. Well, what that means is that 20% of the observations in my data set are younger than 30, or perhaps equal or younger than 30. So, in other words, um, we're going to see that 25% of my data in that case is younger or less than 30. Conversely, that means that 75% of the observations must be older than 30 or equal to 30, right? So if we have a bunch of observations that are exactly equal to 30, that makes this a little bit more complicated to interpret because we have to decide, are we going to round up or round down, basically? But that detail isn't so important for us at this stage. The main thing to recognize is just that this basic interpretation that if you're at the 25th percentile, then that means 20% of your observations are at or below that point. So, how do we actually calculate this? Well, usually we can just rely on software to do this. But if we were to do it by hand, To find the pth percentile, we're going to line up all the data in order from least to greatest for that variable, and then pick the value that marks the p% point in that lineup. So, for example, if we're looking at the 50th percentile, we're going to pick the middle observation after we've lined everything up. There are various methods that can be used to deal with ties. Like I said, if we have a bunch of observations that are equal to 30, or with rounding, other things like that. But we're not going to worry about learning those different approaches in this class. There's not one way to calculate a percentile if you have to deal with ties, for example. But we don't care so much about those details. So let's look at a practical example. This is a graph that comes from the Census Bureau, and it is reporting until several years ago now how household income has changed over time at different percentiles. So let's start with the 50th percentile, which is also called the median, as we'll talk about in more detail later. So one way we can interpret the 50th percentile is that's just kind of the typical household, right? 50% of the population earns more than the median, and 50% of the population earns less than the median. So it's kind of a typical point. So we can see that in the late 1960s, the median income was about $44,000. And more recently, it's around $53,000. So the median income has increased just a tiny bit, but not a lot. If we look at the 10th percentile, now we're looking at some of the poorer people in our society, right? Um, at the beginning of this time series, back in 1967, they earned about $10,000 as a household per year. And in more recent years, we see that they've increased just a tiny bit to about $12,300. So, in other words, part of what we're seeing here is that income has not risen that much over this time period for these lower percentiles. What about the upper percentiles? The 90th percentile, right? Now, remember again, the 90th percentile is, if we want to interpret that at the beginning of our series, this is saying that 90% of the population earns less than $93,000 a year, right? If we round. So that means conversely, the top 10% are earning at least $93,200 a year. How has that changed over time? Well, by 2014, the top 10% are earning at least $157.5 thousand a year. So you can see that income has really risen pretty dramatically for those top groups, right? Those top earners. The 95th percentile, we see something kind of similar, right? So this is one way to perhaps depict rising wealth inequality or income inequality in the US over time. You can see that income goes up just a little bit for the lower ends of the distribution, the middle part of the distribution, but for the high end of the distribution, there's a really dramatic increase in income over this time period. Just one practical example of how we can use percentiles to learn something about what's going on in data. All right, let's talk about histograms. Histograms are a type of bar chart, and there is a little bit of explanation here about how bar charts work. But let's return to this in just a moment. I think it's easiest to just look at a couple of examples. So, first of all, this first example is showing how histograms look with qualitative data. Here, our qualitative variable that we're examining is gender. And we just have two different values that this takes on in this particular data set, male and female. And we want to know how many observations in our data set are men and how many observations are women, or to be a bit more precise, how many are male and how many are female. And you can see that there are around 70, 72 observations that are female in our data set, whereas there are only about 55, 54 observations that are male. In other words, there are more females than males in this particular data set. That's the kind of thing we can see with a histogram. Let's look at another example of a histogram, and this time it's going to be oriented the opposite way. This is showing how large of a tip someone received. And you can see that there's all kinds of different values ranging from around, between 50 cents and $1.50 all the way up to around $10. And you can see that most tips, though, seem to be around $2 or $3 in this data set. But there's quite the range. So, having looked at that, let's go back to the definition or the description of a histogram. Each bar that we see is going to represent either a single value, like if we're looking at a qualitative variable in this in the example that we just had, that would be male or female. Each one bar represents male, one bar represents female. Or it can also be the case if we're looking at a continuous variable or a quantitative variable that we're going to have a range of values, which is also known as a bin, that's going to be represented with this bar. In other words, this bar right here is representing not just a single value, but any value between about 50 cents and about $1.50, right? And I say approximately because we can't tell exactly where the cutoff is because we're not zoomed in enough to be able to tell exactly if the edge of this bar is $1.49, $1.47, or $1.50 exactly. But you can see that this bar is representing a whole range of values, about a dollar range, right, from 50 cents to $1.50. Um, so again, we call that a bin when we're looking at that. And the height of each bar is going to represent how many data points are equal to the corresponding value, or how many data points fall within that range of values, that bin. Now, one other thing I want to show you about histograms before we move on is that we can get pretty different results depending on whether we draw wide bins, right? Here we said the bins are about $1 in width versus if we draw very narrow bins. Here is an example of that same data as in the prior slide being drawn or being graphed with much narrower bins. And now we can get a lot more detail, right? We can suddenly see that there aren't a lot of tips that are around 50 cents or 70 cents or 80 cents. Instead, it looks like there are a lot of people that are tipping $1, right around $1. Now, there's still a bin here, so we don't know exactly if they're tipping 95 cents, 96 cents, 97 cents, or exactly $1. But if I had to guess, most of the observations in this bin are probably exactly equal to $1. And the reason I say that is that if we look at this more broadly, we can see that there are um, a lot of spikes, right? The tallest bars tend to be those that are relatively whole numbers, right? Or that include whole numbers, right? So we can see that this bin that includes one is much taller than the bins around it. The bin that includes two is much taller than the bins around it. The bin that includes three is much taller than the bins around it. So this suggests that a lot of people like to leave tips that are whole numbers. I can understand that. That's what I tend to do when I tip. Although you can also see that there also are sometimes spikes at 50 cents, right? So $1.50 seems to have a lot of observations. $2.50 seems to have a lot of observations. Not quite sure why there seems to be a spike at something like 7.70, right? I'm not sure exactly what value is happening here, but it looks like there are some exceptions. But for the most part, we're seeing that the bar tends to be a little bit higher when we're close to a whole number, right? When we have contain 3 or 250, for example. So, which of these two histograms is better? I would argue that they're both great graphs. They just show us different things, right? So this gives a more detailed, granular look, whereas the previous graph is more looking at the big picture, right? Telling us something about most people tend to tip $2 to $4, but we don't really know which values within that range. Whereas if we draw the bins more narrowly, now we're able to say, oh, it looks like a lot of people are tipping $1.50, $2, $2.50, $3, $3.50, $4, and then quite a few tipping $5, right? So we can be a little bit more descriptive when we have narrower bins. This is just something to be aware of, that the wide bins don't allow you to find out exactly what values are occurring frequently in the data set, just what kind of range we're seeing. All right, let's look at another type of graph, a box plot. This is going to be a useful method for depicting continuous data. This isn't going to work for qualitative data. Um, the histogram can be used for qualitative or quantitative data, but the box plot is only for quantitative data and tends to be especially useful for continuous variables, the ones that we can measure to lots of decimal places. Although I'll say this isn't on the slide, but it also tends to be pretty useful for discrete variables, whole numbers. Um, it's going to be especially useful if we want to make comparisons because we can put two box plots right next to each other in a way that's not quite as easy to do with histograms a lot of times. Um, what is a box plot? Well, let me show you one, and then we'll come back and talk about the details again. You can see that there's two box plots here, and we're looking at a data set that records the number of times that college students report binge drinking within the last month. And binge drinking is defined based on how many drinks they have, and it's going to differ the exact number of drinks that constitutes binge drinking depending on if you're male or female, the sex of the individual. And so here we can see that um, the number of times in the past month that these college students who were male binge drinked tended to be around 5 on average. And we'll see this on the previous slide when we return to it, but this middle line right here represents the median. In other words, 50% of the observations that individuals binge drank more than this many times among the males, and 50% drank fewer than, I think this is 4, fewer than 4, binge drank fewer than 4 times in the past month. Among the females, we see that the median is slightly higher. It looks like it's 5 instead of 4. And so the females in this data set are actually binge drinking a little bit more than the males. And maybe that cuts a little bit against stereotypes, but we should bear in mind that the definition of binge drinking assumes that males can drink a larger number of drinks before it becomes binge drinking than the females. So, um, that's an example of a box plot. Let's read a little bit more details on it. Like I said, the middle line is going to be the 50th percentile. The edges of what's called the box are going to be the 25th and 75th percentile. What do we mean by the box? This region right here, the part that's colored in with blue, right? So this is the box, this is the box. And so we can see that the 75th percentile for the male and female seems to be pretty much the same. The median is a little bit higher for the females than the males. And then the 25th percentile is also higher for the females than the males. So it actually seems like the things are a bit more compact for the females in terms of the box. This is a smaller box. So 50% of the observations are going to be between the 75th and 25th percentile. So we can say 50% of the data falls within a little bit narrower range for the female respondents than the male respondents. Right? What about the whiskers? The whiskers are these lines that come out on the edge. The whiskers are going to indicate the range from the maximum and minimum values that we observe. Although, a lot of times when we calculate this range, we're not going to use the absolute maximum and the absolute minimum. Instead, we're going to exclude what are called outliers, which just mean extreme values. So you can see here that there's at least one respondent who, among the males, who says that they binge drank 20 times in the last month. That is not being counted for the range. So the whisker, instead of coming all the way out to 20, is just coming to 15, because if we exclude this outlier, or maybe there's more than one outlier right here, could be more than one person who said 20, then at that point we can see that the maximum among the remaining respondents, if you exclude the people who said 20, is going to be 15. So again, middle line represents the median. This box right here represents the range from the 25th percentile to the 75th percentile. The whiskers are going to represent the range from the minimum to the maximum, excluding any outliers that we'll just represent as individual dots. So that's how a box plot is drawn. Most of the time, we're just going to ask software to draw a box plot, and it's going to do all of this automatically for us. But it's helpful to know what's being done so that we can interpret a box plot correctly when we see it. All right, a few tips for graphing, and in particular, I want to highlight some graphing pitfalls, and there's more details on some of this in the textbook. Usually, simple graphs are going to be better. Sometimes, software may make it really easy to do things like 3D graphs, But a lot of times 3D graphs are not actually going to be that useful. They're going to be hard to understand. They could even be a little bit descriptive, or sorry, a little bit deceptive. So usually sticking to simpler 2D graphs is going to be a better approach. With histograms, be aware that the graph might look different depending on how the bins are drawn. We already saw that example where with the tipping, where if we draw very narrow bins versus wider bins, we're going to see a histogram that looks kind of different. Another point to know is that if you where you start the bins can also make a difference, right? So we saw the first bin, if we come back to that initial histogram, seems to start around 50 cents. Well, the histogram is going to look a little bit different if we decide to start the histogram at 75 cents instead of 50 cents, right? So just be aware that you can get histograms that look kind of different depending on the exact way that you're drawing those bins. Very important to pay attention to how the axes are drawn, the X and the Y. And in general, this is one of the biggest mistakes that I see made when people are looking at creating or interpreting graphs is that they don't pay close attention to the X and the Y axes. So there's a great example at this website, and we'll go over some additional examples when we are in person together going over some exercises. But for now, just know that the axes are important to pay attention to, and we'll return to this topic in the future. All right. Final thing I want to show you on these slides. This is not, material that you necessarily need to be studying when it comes to exam time or anything like that. But I just wanted to show you, we focused mainly on histograms and box plots in the main part of this lecture. But I just want to show you that there's some other types of graphs that we can use as well. And we're still looking at the same data of the number of times that a college student reports binge drinking in the last month. But here we're combining males and females together just in one graph. We're not separating them out. So you can see right here that it seems like most people binge drink less than 10 times a month, right? Most of the students, which is good, probably, right? So this gives us a basic idea of what the data looks like with a histogram. But what would we find if we used a different kind of graph? Well, let's look at something called a kernel density plot. You can see this is the exact same data, but it's being depicted a little bit differently. You can think about it kind of if you instead of drawing bars, you tried to draw a smooth line through these bars, you might get something that looks kind of like the kernel density plot. And again, we can conclude that most observations are smaller than 10. Most people are binge drinking less than 10 times a month. Um, Another kind of plot that we can look at is the box plot, of course. So this is that same data depicted as a box plot instead of a histogram, like we started out with. And again, we can conclude that most people are binge drinking less than 10 times a month. In particular, we can say that 75% of people are binge drinking less than, I think this is 8 times a month, right? So because we know that the box part of the box plot is depicting the range from the 25th to the 75th percentile, we can say that 75% of these students are binge drinking fewer than 8 times a month, or maybe also 8 times a month, 8 or fewer times a month, I should say, to be really precise. And again, we can see that there's a few outliers here. Okay. Two more graphs we want to look at with this, again, the same data. This is what's called a violin plot. And you can see that this has some similarity to the box plot. It actually shows a box plot in the middle. But in addition, we get this violin thing going on here. And it's just going to be wider from top to bottom at the spots that have a lot more data. So kind of like if we have our kernel density plot, but then we add a second version of this kernel density plot at the bottom, right? You can imagine having the kernel density plot, copying this, turning it upside down, and that would look kind of like the bottom half of this violin plot. And then one final type of plot is called the strip plot. And just each one of these dots represents one observation. And you can see, again, most of the observations are less than 10, though we do have a few observations that are greater than 10. So 5 different ways to graph the same variable. And all 5 of these are fairly common types of graphs. So just want to give you a little bit of familiarity with the range of ways that you can graph data. There's always lots of alternatives to how you can graph data. So hopefully this was a useful introduction. Of course, we could talk about graphing for a lot longer than the few minutes that we had for this video, but I hope that it gave you a good introduction.